So I'm going to introduce Benedek, which I wasn't well prepared to do.
Thank you, though.
Because I met Benedek 6 or 7 years ago, I suspect, when I was in Budapest. And was introduced to him through a mutual friend. And I was very intrigued at the highly anthropomorphic hand that he was working on then as a PhD student at the institute, which
It's
institution?
Plasma University. It's Faculty of
I don't have to
Biomechanics.
say it anyway. So I've kind of followed what he's been up to in the years since that time. He's the CEO now of Allonic, which is a company to produce a hand that he's going to be telling us about, which again is a very impressive hand with respect to how anthropomorphic it is. And he contacted me because he was coming for Rehab Week, which at least many of you know, is actually done in Chicago. So we had a good opportunity to get back together again and through a number of mutual acquaintances, set up this talk for it. So anxious to hear what you have to say.
Thank you, Lee. And yeah, well, thanks for bringing all the people together, and thank you all to Kevin and Mitra and every one of you for the opportunity to be able to present our work here. So yes, so what I'm gonna be talking about is indeed a hand and everything that comes with it. It's about biomimetics. So we are working in biomimetics and the technologies that enable them, the technologies that make it possible for us to create such biomimetic structures. So but before that, so then our first introduction, so yes, I must correctly there because I'm not a PhD. I did my bachelor's and master's at Plasma, and then I studied at K Leuven and I interned at Shirley Ryan. That's thanks to Lee at Levi Hargrove. And then when I got back and we kind of handled the pandemic situation and we could go back to work, I started a research group which turned into a prosthetic lab. And then we spun off Allonic when we kind of went in this direction with this technology to make it available and to commercialize it essentially, which I am now the CEO of. So I'm an engineer originally of bionics at heart, mostly mechanical engineering, not too much electrical engineering and some computer science. So that is kind of the background there. So the research interests we are working on are focusing around like two great areas. The first one is biomimetic robotics for various applications, but what we're interested in, be it prosthetics, be it humanoid robotics, teleoperation, whatever, is how to make it more natural. If we could somehow approach, for various reasons, which I'm going to talk about, of course, if we could somehow approach the human likeness of our own bodies, how can we do that? And for this reason, I'm also interested in production technologies, mostly involving textiles, field boost technologies that could somehow bring us closer to replicating these tissues in a way that's actually industrially feasible. So that is always a target, and was always a target with our research, to build something that we can do. So I'm going to begin with some history to like kind of introduce you to the journey that took us to where we are now, and then talk about where we actually are now. So it all started with prosthetics. So it was kind of a bachelor's idea that as a student, that I really thought that perhaps with some ingenious mechanical engineering and soft materials, we could somehow bring these two things closer to each other. So I couldn't really imagine, embodiment is a big problem with prosthetics. So most of you are probably familiar with that. There are a lot of great innovation going on in control technology, hand design, etc. But it's a great problem that it doesn't integrate well into our bodies. We don't feel it as part of ourselves. It's an extension, it's a tool. So, and part of that problem is because how unnatural it is. So I was figuring that if we could make the motions more natural, the texture, even the aesthetics, not necessarily like uncannily human-like, but in terms of feeling, maybe we could improve on that. So that was kind of the beginning. And there is a short video to illustrate that, which I very much like. I'm a big fan of the Hero One project for various reasons, two of them being that I love the superhero design. I think it's a great selling point for children. And the other is that they made it actually a lot cheaper, which is a very great approach to accessibility, and prosthetics are usually very expensive. And the capabilities did not suffer much for it. And what I want to highlight there is that this is a very simple hand in terms of control. That is how and mechanics, that is how they managed to keep it so cheap. And what you can see there is the lack of compliance in terms of rigidity, like everything is made of rigid structures, and the control suffers from it. Here she's talking about the difficulty because she cannot bend the wrist, so she needs to tilt in for drinking. So this is a great example of what if such simplicity in design and control could be compliant and could be solved. So the same hand, basically the same principles, the same cost in a softer way. So that is what I'm interested in bridging, like originally. And to the next topic, because I must do this, but I probably shouldn't be around showing this to you, is Dexterous Robotics, of course, which you are more familiar with. We reckon that it was already very advanced at that level when we started it. So the shadow teller operation, which will come up in a minute, was already around. But we figured that there could be perhaps two like very upfront things where we could improve upon this. The first is that if it's a naturally human-like structure, maybe the level of abstraction between control and the actuation could be reduced a little bit to make it more intuitive. And the second is that especially nowadays, when humanoids are starting to boom, applications of softness and compliance are functionally important. And also, if we go towards human interactions, safety is a critical part, because if we have only rigid components, it becomes a control problem a lot of the time. And if we would have the same level of dexterity with compliance, like inherent compliance, maybe we could move towards safer human interactions, which is especially important because we have a lot of amazing companies doing industrial automation as well, but they are trying to bring humanoids into our homes as well. I'm a little bit too quick for this video, I know this, because this is the one I'm talking about. So this is actually 1X with the Neo, I'm sure you're familiar. I like how the approach is that they cover it with textiles to like somehow bring it closer to this area. This is of course not necessarily needed at the manufacturing plant, but there still could happen a lot of human interactions where this could be important. So that's about the motivation part. And then to take a little closer look at the technicalities. So here's a hand we all know. And here are two like flagship products, I think. So the Azure Touch Bionics iLimb hand, which is a prime example of a high quality prosthetic hand, and the Shadow Robot that you also all very well know. What we kind of observed is that, okay, so if looking at it, yeah, sure, they are both our hands, but if you look at one layer deeper at anatomy, are we already starting to see the differences? So essentially, what we identified as one part of the problem is that the mechanics that we're using to try to build something like this, which is an interconnected network of various tissues and various levels, they are coordinated, they are synergistically active. We try to discretize, of course we have to, like from mechanical engineering's perspective, but we still use like the same conventions as industrial grippers essentially and conventional mechanics. So the original idea was, and this is still bachelor's, so we're in the past, that what if we could take this entire thing and try to copy it as it is. And then we wanted to see if we could at least reach similar results in a sense of control, for example. So this hand was the first, zeroth version of the prototype. It uses MRI scan as data source for making the bone 3D models, which are 3D printed, and then laser cut ligaments and the complete tendon system also laser cut is screwed on at certain attachment points. And this was built above 30 actuators. So what we really try to do is to look at muscle activity patterns from ultrasound and EMG, and not a direct control, but just to try to replicate some of that and see how it works in order to achieve like all the benefits in terms of intuitiveness and human-like natural behavior. So this is how it's a really quick demo we did. I think this video is about 5 years old. Like that. So this is a quick video of what we did. It will have some grasping demonstrations. This is all controlled manually. So it has like an interface where we can program like muscle groups and single muscles for control. But what I want to highlight here is that this is like a really easy, there is not much calculations and engineering work done other than figuring out the attachment points, but still the movement characteristics are very nice on the eye. So that's kind of the best way to put it, because of course it's very difficult to quantify this. But what we wanted to go for was this like general feeling of naturality at this level. So yeah, there are certain grasps, and then I don't know if the next one will be there. No, not yet. Yeah. So the main reason behind the benefits is that the compliance is inherent in the fingers, which means that in anatomy, it's not only due to the materials, but also the joints and the tendons, the way they are configured, the variable stiffness they inherently have because of the ligaments stiffening up only in certain positions. It enables it to perform really well in tasks requiring adaptivity. And yes, we of course did try. It's difficult doing it manually, but we did try to like perform some in-hand manipulation tasks for like starters, but then we moved away from like control problem, but because we identify certain other issues which I will bring about right now. But yeah, this is like just a really early stage example for that. So this was the big question. We could do nice videos. It was a nice prototype. We liked the concept. We felt that this feeling part, the naturality, was kind of validated, so interesting to do. But we also figured out that it will never make it into production. So it's impossible to make something like this in this way applicable. So that's where we really got started. That how could we build something that is feasible and has these beneficial characteristics? And so let's talk about these characteristics a little bit. So there were a lot of issues, but primarily with the mechanics, 3 prevalent issues. The first is that with the bones, we had these like meshes because they are based on medical data. So this is a featureless freeform geometry. It's very hard to do engineering on that. There is a lot of great software like Anthropology, for example, to do like associative work. We played a lot around with that. But eventually, at the end of the day, if I build a hand for various purposes, I want to control the degrees of freedom, the ranges of motion, the size of it, length of the bones, joints, everything. So that's a problem. Another problem is fragility because of the materials used and the construction. The silicon, I think on this hand, I needed to replace it like every 2 months or something like that, and it was not in use only for demo, so it's fragile. And the third one is complexity. So if you just look around, but that is, and the two last parts are interesting because that's not only true for our hand, but most dexterous hands suffer from the delicacy of their mechanisms and also the complexity. So the sheer number of screws there makes it very difficult and very lengthy to assemble and very difficult to automate. So it's no wonder why there is huge amount of money poured into scaling humanoid robots nowadays, because they just simply need to have those very complex assembly lines. And there's still a lot of money working for till today. So what we did is we tried to take a look at each of them. And the first one came with the realization that anatomy is actually parametric. So sure, it's an evolutionary optimized system, which kind of grinded itself down, so to speak, to the optimal grasping performance that we required as animals. But the geometry of it was well investigated, and there are certain patterns to recognize and rules to recognize. We can use the geometry to actually the geometry is defining the ranges of motion based on the articular surface geometry and the ligaments. And what we did is we tried to build a system where we do this in reverse. So you feed in the desired parameters, like how big the joint should be, what should the ranges of motion be, how should it work in terms of certain heuristics are known, for example, for the metacarpophalangeal joint, that when you flex it, you lose the ability to abduct and abduct. So this is a limitation, which is an influence the geometry takes on the degrees of freedom. So we built a system where you take these parameters, you feed it into the system. We actually did it in PTC Creo. It's maybe some of you know it. It's a pretty hefty CAD system. You feed in a couple of parameters, basically 8 to 9 per joint. Most of it like joint width, bone length, ranges of motion, distortions, etc. And it generates different variants of the articular surface geometry. So that essentially means that you don't have to design everything when you want to customize these joints. You can just use the system to generate production-ready, so there's actual bones production-ready components. So essentially, you feed in a couple of data, and you wait a while PTC Creo tries to survive the regeneration process. And when it does, you have, after a couple of turns, you have like a fully fledged scatter system ready. So that is what we're using to customize our hands now. It's very important because when, for example, I want to tune in thumb position, that's a very difficult thing to characterize, very difficult thing in the design phase, because I cannot build a jointed CAD system for a saddle joint. It's just not how CAD works. It's very difficult. I could probably do it based on collision, but not really reliable. But I can assemble it quickly, and I can modify a parameter and go to the next version. So we also built, from a medical aspect, an application for this, which is right now a semi-automatic way of getting most of the data out of X-ray images. It's obviously not ranges of motion, but like joint sizes and certain feature extractions we can do via a bone, but actually image fragmentation, where we are finding the bones and the spikes signify the joint areas, and then we can examine the geometry next to it. So this is in an early stage, but we figured that it could be very useful if we really move towards prosthetics one day, to like maybe give you your hand back or your other hand back. So for embodiment, it sure could be something valuable. So this was the first question. The second, and this connects to the third, is the connective tissues. So I spoke a lot about softness, how I always wanted to somehow replicate this. The issue is kind of visible here. Okay, that's not a tendon-driven example, but you see the point that on one side we have a greatly simplified system where we try to, either with linkages or tendons, imitate the joint behavior. And the other side, we have this complex network of tendon system, which is why our hand moves the way it does most of the time. So the primary thing it enables us to do is that on average, we have 6 muscles for each finger, which means that we use the same muscles for different activities. So the muscles that are responsible for fully extending the finger are the same ones that we use for tilting, and the same ones that when we flex the finger, this bulges up, and this reinforces the flexion extremely. So we actually use multiple muscles for different things synergistically, which means that we are able to kind of reinforce the motion intrinsically. So this is a nice thing to have, besides just simply the feeling of naturality. So I think everyone can see the problem with this, and it was relevant to the laser cut version as well. But this is very complex, and there have been some great work done in the previous years that honestly was the primary inspiration when I started this project. This was of Emmanuel Todorov, and to replicate this in a way, to build this, like they use silicon and a few strings. This is a crocheted version, which I tried to do something like this, and I can tell you, oh my God, it's very tedious too. Like, there is no such thing as a crocheting machine in these terms. It's just not existing because it's infeasible. So there are a lot of different options. So, but the problem is that any way you try to replicate these networks, you will run into the issues that if you have elastomers, the material fatigue is great. If you need to connect ropes or anything, you can crimp them, glue them, sew them, tie knots. It's never gonna be, you always have a mechanical weak point, you will always have an obstacle, and you will always, what's the third one? Yeah, it's impossible to scale. So you need people tying knots. That's not a good way to mass produce devices. So what we took a look at is the structure that we kind of stumbled upon from our biological studies, like the close resemblance the collagen structure has with ropes, braided ropes, like your shoelaces or climbing ropes or sailing ropes. So there was an idea that, okay, we like ropes for the same reasons we like tendons. So they are load bearing, you can control this via, so the main benefit is that when you pull on a braided rope, it's able to conform in microstructure. So it means that it doesn't get torn apart so easily when it gets a sudden stress placed upon it, but it will conform first. So there's a reason, for example, the shadow hand already also has braided tendons in it. So it's widely used. We also found this to be a good idea, but here comes the question that, okay, we wanted to do something interesting with this. How many of you actually know, you're mechanical engineers, some of you, so maybe you do, how ropes are made? How does a rope making machine look like or operate? It's a good question, right? Yeah, so it looks like this. And this is the simplest version. This is just a 3-strand braid. But what's happening is that we call them carriers, these pylons, which represent 1 strand each, and they move on a predefined pattern. And our parts around we call them horn gears. Basically gear connected rotators which have slots on them to pass them around. And then you can imagine that if I were to increase the number of slots or put them in a circle or something like that, I could create more elaborate patterns. So that is how ropes are made. Usually not simple like this, but like in a circular pattern, and then you have a cube. But that is basically the principle. And so what we did is that we went to a lot of events to figure out that, okay, how this is, check out the machines. And we found that the Germans actually, about 30 years ago, figured out how to make this 3-dimensional. So what this means is that this here is a switch. And if I turn this off, the arm will not get passed along. if I turn this on, it will get passed to the next one. So by doing this, you can program or you can control the way the yarns are moving. So we played around with this concept, upgraded a little bit, and built a machine on steroids, which is capable of doing like elaborate constructions, three-dimensional bifurcating rope structures in essence. So this is how it looks, and this is how it looks in operation. This is real time right now. So this is the first generation of our breeding machine. And so what is happening is that they are moving along predefined patterns, and it's not on video, but they can what was that? They can stop and reconfigure the pathways and then start moving again. And then inside there, the braid is forming. So
The braid is forming out the top or down the bottom?
it's out the top. But this is how it works, basically. So you see there that this is a bifurcation we're creating to look like this. We call it a button hole, but this is a common term. So that's one track. You can see it with the green switches. And then we switch. Now it's two. And then we switch it back, and now it was joined. So that is the most fundamental part of the thing. But you can go crazy with this. So what we have is, and that's perhaps the most important part, because the brilliant German mechanical engineers not necessarily always care about so much about the three-dimensional aspect of it. They are using this technology is not widely used. They are using it for carbon fiber production for like aerospace or space industries. But they mostly care about patterning, repeated patterning. So there is no high-level control software available that allows you to define your own high-level structures. So what we did is that you draw like a structure that you want to create, and then we turn that into a series of operations, essentially. So bifurcation, joint, juncture, there are certain other operations like pattern changes, travel moves, etc. And then we arrange it in a topology. It's basically like a slicing process, and then that gets translated to actual patterning. So the idea here is that as a user, so right now we are scripting this part. So the graphical interface is just like this is gonna happen next. We are developing this right now, but right now we are working scripts. We are writing scripts to work with the same feature set. But the idea is that as a user, you only want to care about this part and maybe this one. And maybe you want to do some modifications. Yeah, you can go crazy with this. You don't generally want to. So we're working on automatizing all these processes. This part is already fully done. So if you have like a topology where you don't have to know anything about the braiding rules or whatever. So that is the idea. And so we can do all kinds of stuff with it. So these are bifurcations of different patterns, flat braids, pattern changes, various other bifurcations, overbraiding. That's actually elastics in it, so we can make it like a spring. What else is there? Yeah, different. Those I don't even know what that is in the top left corner, but it's something fancy. So the idea was that with this design freedom we have, we can look at the tendon system and identify the structures and the geometries that we need. And so we went around and basically did that. The biggest benefit here is that this is something very strong. So if you look at the cross section of a human tendon, like we're taking the flexor here as an example, that is about this size. We have good scientific work on that to examine the cross section and the relation of the load. And the ultimate load was 170 kilograms, which our flexor tendons were able to support. So that's in the range, absolutely. It's about the same range. And the exciting part is that this is only technical polyester. So we could move for nylon, for Dyneema, whatever. It gets tricky because the reason why we didn't go with Dyneema in the first place, that to fix it to the actuators, maybe you're familiar, the knots simply slip. It's so slippery. Very strong though. So the braid doesn't slip, so we'll figure out something. So what we
Can I
did.
ask a question about?
Yeah, sure.
So, I understand you have different profiles. You can make flatter braids but let's stick with circular just for the moment. What are the things that you can trade off? So I understand you have different braiding pattern possibilities. Do you find that some braiding patterns are stronger than the others in the same cross-sectional area?
Absolutely.
And what's trading off?
There is actually a wild behavioral difference between some of them. So the good thing is that we have a very low number of core patterns. So you can experiment with whatever you want, but the core patterns you will mostly use is very low. It's like 3, 4, something like that. The difference is mostly in the conformation ability. So when you tug on the rope like very strongly, there are patterns that comply more easily, and there are ones that are more rigid. So we usually define this, this is going to be difficult to, yeah, but so we usually define a pattern as when you move to, for some reason, the horn gears are very lightly visible, but when you move along the track, we usually define a pathway by placing ion, skipping ion, placing ion, skipping ion, because you need this for the other pathway to interlace into it. And we can also do like placing 2 yarns, skipping 2 yarns, placing 2, skipping 2. So this is basically full empty rule set. And for example, if you place 1 by 1, it becomes a much more, so it essentially, a braid which looks like this will be a rectangle. So it will look like a flat, but tubular, but flat rectangle, because it keeps it, after a certain size, it falls a little bit apart, so you need to pack it together. But it is a rectangle because it holds very tightly. It doesn't really, it's not really elastic. If you do the 2 by 2, it's much more compliant. You can pull on it a little more, it has more give. So it's more difficult to break, but also you have to account for some inherent elasticity. So these are kind of, but these are, so the lucky thing is that this is known from the industry, because the guys are producing ropes. All they need to do is this, because you have to have like consistency when you're producing like rope by the kilometer. So, but that's absolutely a thing, yes. Yeah. So to continue, this is basically the breakdown of the tendon system. So you can see that, okay, we have the structure design. These are kind of snippets from the different points of the tendon system. And then you have the complete tendon system manufacture. And it's just like a note that for some of these, so topology is great. Most of the job is not happening at the topology level, but in 3 dimensions where the braid actually gets formed. And we are developing machine vision based feedback systems to actually quality control this during production, to keep it consistent for the very reason that you asked, to keep it consistent and detect errors. If we have an error, which is not a yarn break, we are usually able to go back and fix it. So if something gets, I don't know, there is maybe a tiny knot or a mistake in the yarn. So this is why we are doing this one as an extension. But the end result is that we are able to produce these very complex and very strong monolithic structures. So the entire point is to not to have weak points at mechanical junctures. So that is kind of what we did. And that is how we actually built the next prototype, which already has these tendon systems incorporated. And it has a lot of other things like textile, soft tissues and pulleys and etc. I'm going to only talk about for a short while about this, and I have a very short video to demonstrate. This was not a dexterous hand. This also prosthetics purpose. It has 6 motors for the fingers, one for each and for thumb position, but the nature of the movement is the same. So it's still the naturality of its high, and it's very compliant. So the basis of it is that if you grasp something, your fingers will comply around it and ensure like a firm naturalistic grip instead of the vice-like mechanism most prosthetics have. I only have for demonstration like a simple grasping task here, but it kind of illustrates how we could manually move the fingers. And this way, maybe, yeah, so the finger trajectory analysis is also there to show that that is when we just simply try to measure for repeatability. It's not bad, actually. You see like 2 lines, one is flexion, the other is extension. We cannot control the trajectory deeply. In this one, you see 3 different types of movements of the finger, which we did with an advanced actuator frame to illustrate that, okay, this can do the lumbrical activity, the interossseous activity, and like everything, like different postures. So we did a couple of grasps, we tested it on the grasp taxonomy, and it worked kind of well. We really like this model. It's in the black tube, so you will be able to look at it later. But here came the exciting part. That we said that, okay, we could do the tendon system, and it looked nice. It was a very nice process. Why shouldn't we do basically everything else? And so that is what we did. So right now, what you see here in this process is a complete finger being braided over just 4 sets of bones. There's nothing else in there, just the bones, and the ligaments, the tendons, the pulleys, everything is did over it in a single process. Even the cable routing is done during production. So this is a, so I must say that this is a demonstration part. This is a simplified finger model, because for producing the biomimetic one, we need a larger resolution in the machine. That is what we're working on right now. So that is done in 2 parts: joints, pulleys, and tendon later. But then even then, you only need 3 screws for the 3 attachment points. But the idea here is that you don't need to have absolutely anything connecting joints, only the ligament structure. And sweet, that really looks nice. So yeah, so you can see that it has two interphalangeal GR joints. It has a metacarpophalangeal joint. You can see that. So there, this video doesn't show anything because there is such an IP involved in why it would look very nice in terms of what other operations we are doing on the fingers and this in this three-dimensional space. But the basic concept is that by manipulating the topology and relocating the parts, because we're also doing that, so you could see the tendons moving in and out in order to be routed, we can create this structure. This finger is also here with me, because that was the entire purpose of it, to do like a demonstration of our process. And so here it is. I will pass it now. That was a faster. Yeah, so that's a demonstration piece. We didn't really care about the parameters, so it's a little too stiff, and the flexion range is that's not too great, but that's like modifying a number. So that is what led to this next version of the prototype, where everything is done like this. So all the 5 fingers, essentially the only thing you need, besides cheating a little with the screws, because this is done in 2 pieces, to like screw it on the palm and wire up the actuators, and you have a hand, a biomimetic one. And so this is very new work. So we don't have a very advanced control algorithm. We don't have a control algorithm. Actually, we have manual control as well. But the capabilities are what's important here. So I have a mobile app with some joysticks, which I can play around with my caveman hands. So obviously, when it comes to this manipulation, I fall short. But you could see that, oh, that should have been a claw finger, but it doesn't matter. So there was a pinch. This is some playing around with the thumb position. You can see me mess up soon. But so the important part is that it is very difficult to model these systems. So we were talking a lot about biomechanical modeling. There's been some great progress on that, but it's very difficult to model the behavior. But if you can produce it extremely quickly and extremely cheaply with a single process, maybe that's not such a pain point, because you can try and try again, and then you can build model afterwards. So these are a few trials for that.
So, Benedek, are your finger links attached by anything other than the?
No.
No, it's okay, so there's
Absolutely
no
not.
joints or?
You have 4 bones, like 3D printed. That's it.
And how are they even held together while you're?
There's a process of guiding wires along them that kind of held them together. So there's a need for that, but that's enough for like a longitudinal like a pulling force, and that's it. Don't need anything. Yes.
Are the tendons,
Manipulation playground.
are the tendon numbers and locations and approximate amount you have to pull on them, are those also biomimetic?
Oh, yeah, absolutely.
Yeah.
So yes. I mean, what we've so at the end of it, I don't have the exact data for that. I'm sorry, but like the ranges of motion you have to do on the tendons is also very close to. So it boils down a little bit to the design of the carpal tunnel, for example, which we could improve a little bit. So it's a bit more, but it's in the range. Yeah, okay, it looks. So, but a few key things that I really want to highlight about this structure, because it's one thing that it looks nice and it's natural and sweet to produce the first. But okay, you have a design freedom where you produce everything, every complex structure you can design. It's a biomimetic example, but you can design anything in a single process. The other is that the tendons are routed during production, so that further reasons the assembly. But this is, I think, the most important part, is that because the joints are done this way, so what the single most pressing issue was with biomimetic design for everyone previous and for us included, is that if you attach the ligaments and the tendons, that you're going to be having a point of attachment, which will be the weak point. And there's just nothing you can do about it. And this part is that here come the ligaments, and they wrap around the bones. So when you pull on them, you don't have a single point. It gets distributed over a relatively huge surface area. A composition made of rope-like material that was made for pulling. So I'm not sure how you could get stronger than that in a sense. Of course, I could have multiple layers. So that is, I think, the most important part. And of course, you can have the variable stiffness properties because of the conformability. We are able to integrate elastics, but you don't even have to in this part because the slight conformability will allow you to stiffen your joints up when you flex if you have the proper bone head geometry. So basically, just to highlight that this is how the process looks like. You like this drawing. It shows you everything that you need to do for this entire thing to happen. Right now, producing one finger takes about 3 hours, give or take. because we constantly have to manually make sure, because we don't have the machine vision algorithm ready to that it's doing well, and there are still some semi-manual steps. When we scale up, we hope that with the next version of the machine, this will be below 1 hour, and the calculation show that it will be less, but I really don't want to upsell this because I'm not sure. But so the idea is that because we could eliminate most of assembly so the production, the number of components, the assembly, we could reduce production costs for robotics requiring this kind of biomimetics, softness, or actual behavior by origin. Because of the software, we are trying to do a low barrier to entry, so you are able to like design whatever you want if you don't have like grading technical knowledge. You just have to know a bit of robotics, obviously. And of course, the inherent softness and bio-inspired design are also advantages which for certain applications I think are quite beneficial. But maybe what I also wanted to show you, because this is something that we like showing around, is that this is what we could gather about the production value chain of like a conventional industrial manipulator, like a shadow hand, for example. So you have like a basic linkage system made of metal, with all of the components with their own machining pipelines and logistics and then storage and shipping and etc. You have plastic parts, you have guides and pulleys made of ceramics and Teflon, PTFA, sorry. You have your tendons, which you need to prepare. You have your soft tissues if you want. And then, of course, a whole bunch of fasteners. And then you have a whole meticulous assembly process, most of which is manual oftentimes. And that is how you get to the complete hand after actually wiring. So this is cut off at wiring the actuators, and this is one the actuator part. And instead of this, what we can do is basically looking like that. So you have your bone structure, you prepare those for bleeding, you bury the entire stuff over it, and then the assembly takes you about 5 minutes to like screw the bones on, and then wiring the tendons. Sure, that's something that needs to be done, and that's the other part. That's not the part of kind of the value proposition for production. So this is kind of how the process looks. And you saw the machine in action. That was the first version, and we're already building the new one. It looks like this. And yes, it's a little laggy, sadly, but what you see here is basically 5 times the speed of the module diameter, which means that in the same space we can do 4 times the resolution. So that means that we will be able to scale up from 100 yards to 300 or 400, hopefully. Such a machine will fit 300, but you can use more with smart better. Yeah, and this is, yeah, of course, this is the So this is kind of where we are now, and we will be very happy to explore like potential applications with you, not just for the hand, here for the hand, obviously, but not just the hand, but any other finger designs. Or the idea here is that if we, yeah, sure. I will just. It's just for demonstration, you know, as a nice noise. So what the idea is here that once we scale up, we can of course use a larger yarn. What we are aiming at is to be able to overbraid like something the size of an arm. So we already having talks about how maybe this could be used also for wearables, but like in a robotic arm system perhaps too. So this is kind of the target. And we'll see where it goes from there. Yeah. So with that, I would like to thank my wonderful team. This is right now how we spun off from the university lab into a startup, and really this is mostly because of them that I can be standing here today, because this was a nice job in the last 2 years. So yeah, thank you for being here, and please.
So can you also weave a continuous skin surface, or what are you thinking about actually finishing?
Yeah, for the skin, I'm not sure this is the best approach. If you have a high enough resolution, sure, but you need to think about like connecting the fingers, for example, because the mostly branching structure is difficult to do in this little size with 4 fingers continuously. And this is made primarily for load bearing, not surface quality. So that would usually the resolution in terms of yarn size is much finer if you go, and it wouldn't make sense for this technology really. That is for like pre-produced fabric, and we can do a lot of magnificent things with it. Yes. Oh, sorry.
No.
Can you repeat again, how many in your actual prototype, your demo model, how many motors do you have driving?
Yeah, oh, sorry, I didn't talk about that. In the demo hand, we have 16 motors right now. So 16, yes. So, oh, actually, it's over here. So I can also pass it around, as please don't have it.
Yeah.
But this is the only one we have.
Oh my gosh. Breaking.
Yeah. Oh, sorry.
So I couldn't see why you.
So, yeah, so, right now it has 16 motors for the sake of being able to put it in like a sleek wireless design. It has tiny coreless actuators with worm gearboxes. So what's maybe interesting is that right now that mechanism that on the level of the actuator is absolutely not back drivable. But still, if you try to flex the fingers, it's really compliant. So yeah, that is kind of shared benefit. Of course, if that's not under tension right now because I'm putting it in a tube, but if you put it on under tension in flexion, it gets a firmer grip. Of course, so this is a very first version, so there's a lot of things to optimize in the design, but the idea is there.
Just as a non-hand person, roughly how many muscles?
The total muscle count, if you separate, like, for example, the big flexor muscle, which is a single muscle differentiating in 4 directions, if you separate those, it's 37 for the fingers only. So we do, but okay, but one motor has like 2 different directions, so you can multiply the 16 by 2 with some dependencies, and that's where we're at. So it's not bad, but you can go higher.
I noticed that in your demo, the thingy and the ring fingers move together as a part of the biomimetic structure, or do you just have one?
Right now, no, they can move separately.
Okay.
We have a single extensor for them with a differential mechanism. So that is a shortcut we took for this.
They do, I mean, they are coupled.
Only in extension.
Most of this.
On, no, they are coupled, so that is why we took the shortcut, because it's somewhat biomimetic, but it's not.
Okay.
Swiss?
Yeah, thanks for the awesome talk. I had a question more about the types of fibers you're using. So I know in certain knitting machines, you have some very specific mechanical requirements you need for the fibers, and as y'all potentially think about other types of materials to use, what sort of material properties are required for this process?
For the current version, we're limited by size. So like, it's not measured in diameter, Btex is the name of the parameter, it's from textile technology and don't even understand it properly. But that is the main limitation. And there are certain materials. So the idea is that, for example, with the machine, we could, in theory, of course, use composites, but that would require a different carrier because the properties of the yarn are different and they're more delicate materials. So yes, there are a couple of subtypes. Right now, we are able to work with these kind of technical textiles of like polyamide, polyester, whatever. We're trying to experiment with different ones. Smaller ones, ideas are there for composites and conductive and maybe thermoplastics that allow you to post-bake them and make them semi-rigid, because that would be very interesting to have like semi-rigid layers incorporated in the structure. Conductives for the sensorics. We haven't tried all those things yet, but we're kind of looking to find focus and what we should experiment with.
We have a question online. It looks like, first of all, can you just confirm the fingertips are biomimetic and what properties, friction and compliance, et cetera, are mimicked?
Okay,
And
great.
then also it looks like the tendons are routed through the braided sheath with virtual pulleys.
Yeah, last part.
Let's go with the first one.
Okay, so the first one is that the fingertips are not meticulously designed yet. So that is made of TPU to enable some kind of grasping, but we don't have sensorics integrated yet, and we don't have any like elaborate surface qualities determined for optimal grasping or manipulation. That is something we will need to do. So they are biomimetic in shape, and we try to go for some level of softness that could be similar with the infrastructures of the TPU, but that is really just like a first design. We will definitely have to do a lot of work on that. And I didn't get the other.
It looks like the tendons are routed through the braided sheath with virtual pulleys. How does the friction look on this mechanism? How much fingertip force can it output?
Absolutely, it's a very good question. Right now, it's definitely one of the largest shortcomings of this model, that because of the low resolution we have on the machine, the braid is not compact enough. So we would need to make it more dense in order to reduce friction. And we would love to make it 2-layered in order to reduce the edges that it has. And that would very much increase the slipperiness of it. The material itself is good in these terms of characteristics, but the braided texture, of course, adds a certain resistance. We don't have specific measurements for that yet, because as I said, it's very new results, but the fingertip force we can produce. So we have about 40 newtons on the tendons when we move at about half second for a full flexion, and at this stage we calculate. So we did. It's difficult to measure for us because we don't necessarily have all the appliances, but we did get to about 15. The biggest problem is an extension. So when you try to pull out the tendons of the pulleys, if there is not enough stiffness and if your lever arms are not correct, then it's becoming hard.
Thank you so much. Great presentation. I love that. To me, it seems that the braiding process is kind of sequential. You start from the fingertip and then you go braiding through the hand. I'm kind of challenging you and asking if you also envision a future where the braiding goes in different direction in a circular way. And if you can think about maybe 3D printing through braiding, like in all directions, is that something you've been thinking about?
It's been compared to a lot to that actually, but like so that is one of the main characteristics of braiding, that it is a longitudinal structure. There are options to break it a little bit, and we're also experimenting with stuff like that. But in the general sense, it will stay a longitudinal structure. I do have in my wildest dreams visions for like machine structures moving around and doing something extremely crazy. I'm not currently seeing that as something feasible, but who knows?
So I could imagine as a finger designer saying, look, okay, I want this kind of stiffness in this joint and this kind of stiffness in that joint and some properties of the tendons. Give me a knit design for that. Maybe they're told these are the constraints on what the knit can do, but they're able to play with those parameters. What is the extent to which you can sort of automate my design specifications into a knit pattern?
If you're talking about these kind of design specifications, that is the perfect question, because that is, I think, the best and hardest part of eventual automation. We will, so most of the time when in these type of industries, when they do benchmarking, they perform measurements on specific specimens, basically. So they try to build a lookup table for it, essentially, and then based on that, be able to suggest a certain design or a certain density or something like that for the user. So a lot of it, because the three-dimensional part is so, but it's controlled, but also very chaotic in a sense that the yarn will behave however it wants to in the physical space. This is something you usually do through samples, like you gather the data, but we are very much hoping to build into the system like some levels of this kind of automation, so you can get a suggestion. I don't think that you can completely eliminate the need for testing in a sense. So it will not be like a rigid actuator which you can meticulously design. So textiles have been compared, like for example, if you want to simulate in finite element, like a rigid screw-based metal connection, sure, try to do it at the stage. So there is absolutely a difference there, but that is why we're trying to make it really quick and cheap to produce. And that is something that okay, I mentioned the duration it takes. Right now, the production cost of that hand you're holding, the hand itself, I don't care about the motors, is below $50. You need a couple of cents for the yarn, really. You need to feed it in the bones, you get the idea about the price of that. And then you need to operate the machine. It's a high performance machine, so it takes up some juice, but it's, yeah, so a couple of bucks. So that is what we're looking at. And this is kind of coming from a rapid prototyping mindset, in a sense that we just want to produce and see what works. So by allowing you to iterate quickly, we're hoping that you can, even if we don't have a certain specification or automation, we're hoping that it can be discovered with relative ease.
You've been looking at any like different control strategies. I mean, you only showed us, right, the one with the 6 degree of actuation. But if you were to actuate everything like a hand can, for example.
The answer is that is one of what's coming up next. And we've been talking to a lot of guys about what we could do in that sense.
We're gonna hook it up to the brain.
Thank you. Yeah, so it doesn't get crazier than that, I think. But yeah, that is what we're looking at. The mechanics are there, and even the control is there. So I haven't, maybe if you paid some attention at the fibbling around I did with the ball, there was also like this glow finger opportunity. But the truth is that with a few fingers, this is very difficult. So you're well aware of that. But in theory, this model should already be able to do a lot of things. And we want to experiment with it in this sense, because that will help us figure out the shortcomings, because it definitely has many suffers. So The important part maybe, and that's also something to highlight, is the quickness of the prototyping process. So right now, I said that it takes about 3 hours, maybe for a larger design 4, to produce an entire finger, like tendon and everything. The middle finger of that one was done in about 3 iterations, and all the others only took 1 because of the parametric system. So we're hoping that when we solve these problems and experiment with it, we will figure out what we need to change. And we're also hoping that these will be changes that we can easily incorporate. But what we're really trying to do now is to build the next machine and enable us to do it much faster and much easier and in much higher resolution, and to experiment with different things.
This was just mind blowing, just a fantastic presentation. But I want to go back. You've been working, with structures like these for a while, and using them to provide all of the constraint functions, not just the tendon functions, but the ligament functions as well. When I think about ligaments, I get very afraid because it's hard for me to understand how they work. I wonder if you can just sort of share some of the insights you've gained into how to provide the proper constraints, to something like a finger joint. What are some of the keys there?
Absolutely. So what we figured out, or what maybe the most exciting part, is that about 70 to 80% of the job is done by the surface geometry. So the ligaments really just keep it together. For example, with the metacarpophalangeal, you can pull it apart. It's not even in biology is the same, but it's not even a tightly fit joint because it would prevent it from operating the way it's intended. So the ligaments are constructed in a way, and that's why they are a flat-ish structure, that the articular surfaces they have like an oblique sides, for example. And when you bend the finger, that increases the distance. So it stiffens up essentially. And that way you only need to, so that is how we have the algorithm basically for the articular surface design. We not only design the surface, but the entire bone. That if you control these angles, you control the stiffness. And of course, I don't have like a specific curve for it, but the idea is that you do it this way, and then it just lays flat on the surface and you're aware of the direction. And if you make it longer and have a certain laxness, then it gets more complicated. But that is kind of how it works. And the other very important part is that what we had insane difficulty with at the beginning, before moving on to this design, is that if you have a point-like attachment for a ligament, it's one thing that is not optimal in terms of mechanical performance, but it doesn't really work because these are areas in biology which are grown into each other, and that is why this kind of fan-shaped structure is very good, because if you move, you put a little bit more strain on certain parts of it than the other, and this allows you to do that. If you don't have that, that is why our silicon ligaments usually tore apart, because you needed to somehow pull. So this structure actually does not fix the ligament source area in place. It fixes it here.
Yeah.
And the structure holds itself together, and when you pull on it, it holds it even more tightly.
Yeah.
So in the hand, you can see that some of the coatings of the blade are a little bit lax. We don't care, because when you pull on it, it stiffens up, and it becomes a stronger joint essentially. So that is kind of the source of the idea that is why it's beneficial. So these are the 2 main points, I think. And you always, with ligaments, you always have to account for a certain laxness, a little bit. These joints are rather stiff, but especially when you flex them. But because you want them to stiffen up when you flex them in extension, they're a little lax. And actually, in the human finger as well, the complete stiffness of it is not done by the ligaments. So very much of it is done by the skin, actually. So it's very exciting when you take a hand apart and then you remove the skin, it becomes very floaty. So there are a lot of components. Like that is why I like this design, because it allows each layer to work synergistically for not just their own dedicated purpose.
I don't know the extent to which it's true in the hand in particular, but another function of muscle activation, in fact, is to unload the ligaments.
Yeah.
So the legs don't have
But
it.
it's very interesting in biology. I think this ligament or these ligaments are, I don't have the exact number, but their tensile strength is very low. You wouldn't, a few kilograms or something like that. So you wouldn't expect that especially for tendons with like hundreds of kilograms, but it's low because you don't essentially need it when you actually put stress on the finger. You're using the tendons and the distribution mechanism of the torso. Yeah, absolutely.
We have another question online. The carpal bones are similarly enmeshed in complex tendons. Are you looking at wrist development at all, or is that future work for Allonic?
We are looking at wrist development, but we're not looking at it at the level of the carpal bones because the sheer complexity of that. That is so small. The trapezoid is done that way. So the saddle joint we have enveloped. But for the other parts, we're looking to do like an extrinsic design. If you put a coating on the exterior of the wrist, it's even possible to have something like the carpal bones. Imagine like having a bunch of balls in a sand. So it's similar actually in biological design. So you can move it around in a similar way without having to have like hundreds of ligaments inside by having something well constructed, which I don't know the answer for yet on the outside. So that is future work, yes. But it's interesting.
I think we're at the hour.
Oh, sorry.
And yeah, I think we have to hold off further questions. Maybe you can do it after we thank our speaker. Thank you.
Thank you.